Thank you all for your interest in my presentation about data-driven image generation for crop growth modeling. As Katharina said, I'm Lukas, and I'm going to present you today how we can generate realistic images of future plants. But first, let's maybe talk about why this is needed at all. So the goal of crop growth modeling is to model the development of agricultural plants over time. And what you can see here is the growth development of wheat from germination to senescence. And in crop growth modeling, we now might be interested in, based on an initial state, how the crop might look like in a week or in more than a month. And thereby, growth can be modeled very differently. We can either model the phenotype of the whole plant, or we can just model certain so-called plant traits. And these traits are, for example, the height of the plant, the leaf area, or the grain sizes, which then all can lead to the final yield. The problem is now, although it's quite well known which growth stage follows the other, the date when a certain stage is reached is really not so clear and is highly variable. So if there's a crop growth model which can estimate this, it's very beneficial. And actually, crop growth models are beneficial in many ways. So first, they ensure planning security of actions in the field and improve the farmer's resource use. Second, optimizing resources obviously comes also along with cost reduction, but also better planning reduces costs since it allows to negotiate better market prices and reduce storage costs. And third, and this is maybe the most important point, crop growth models allow for early in-field interventions, which means if the model prediction is not as desired, farmers can go into the field and try to improve the prediction with targeted and location-specific actions in the field. But crop growth models are also helpful in research, for example, to develop new and modern farming practices. And the new farming practice we have explored in PhenoRob are called crop mixtures. These are fields where two different crops are grown together, in our case, spring wheat and faba beans. The advantage over a monoculture is that they optimize the yield, but also the biodiversity in the field, which is quite important, for example, for pollination. However, since we have a great heterogeneity, as you can see in the image, it's extremely challenging to develop a crop growth model. The classic way to implement a crop growth model is the so-called process-based crop growth model. And in Bonn, the modeling framework Simplace is used for the mixtures. It is called process-based because a lot of expert knowledge went into implementing a functional relation between all the processes influencing crop growth. For example, they built a connection between the nutrient uptake and the water requirement and the photosynthesis activity for different crop species. And then given like specific influencing factors, they can predict certain target parameters like the biomass. And the cool thing now is they can do this not only for a single date, but for every date in the growing period. But of course, these models do also have limitations. Typically, comprehensive calibrations with manual measurements taken in the field are needed. And also it can happen that important influencing factors are just not available, or that the functional relationship is not fully correct. And also this is more likely when we talk about the complex field environments we are investigating here with our mixed cropping systems. And finally, which is maybe the most important thing, is Simplace make no use of large-scale field observations. But this is something we can nowadays do quite easily using remote sensing. For example, we can use a drone equipped with a camera flying autonomously over our field. And this way we get information about the heterogeneity of our field quite fast. And when we focus on the interesting field area, like we can directly use this data to train a machine learning model to predict the future biomass in a data-driven way. And in this case, it's the future biomass ratio. So green means there are more, green means there's a spring wheat monoculture, blue indicates fava bean monoculture, and the different red tones are the different mixture ratios. A bit more challenging, but still feasible, is to predict the total biomass from a growth stage close to the harvest date. And this we can again do for individual regions in the field. So for a spring wheat plot, for a fava bean plot, and also for a mixture plot. So this is already a valid data-driven crop growth model trained end-to-end with training data obtained in the past. But it's not exactly what we aim for, because we want to generate an image of the future field. So instead of directly predicting target traits from image data and associated factors of influence, as you can see here on the left side, we go for indirect crop growth modeling. And this means we replace the prediction model by an image generation model to get an artificial generated image as output. So in other words, we try to answer the question, what is a probable future above ground plant phenotype? And once you have this generated image, you can apply several other downstream tasks on this image in a second so-called growth estimation step. You can try to estimate the biomass again, but you can also perform, for example, a detection algorithm to count the bean plants, or a segmentation model to get information about the leaf area. And this is already one of the main advantages of indirect crop growth modeling over direct crop growth modeling. So the generated image can be considered as artificial sensor data of the future above ground phenotype, and thus can be flexibly used for different tasks. The second one is that they visualize the spatial crop growth development. So while classic models just have one prediction for the whole field, the generated image show exactly where, for example, more fava bean plants grow, or where more wheat plants develop. And this is, of course, of high value for targeted actions in the field, but also interesting to understand the mixture dynamics in the field. And third, compared to direct data-driven crop growth modeling, which is essentially a black box model, at least without additional model explainability tools, the generated images offer this explainability for free, basically, because user can, just by looking at the images, better understand and evaluate the final model output themselves. So today I will focus on the image generation part, although you will also see some growth estimation results, because we need this second, so the bottom part of the figure, to evaluate the generated images. And especially today, I would like to focus on 3 papers. In the first one, we did temporal image-to-image translation, where no factors of influence are considered. In the second work, we extended the previous approach to sequential data. And in the third, we finally include factors of influence and run a multimodal image generation. As you can see, I will show you results from different data sets, which also represent different environments and measurement systems. So cauliflower images from a ground robot on the left side, and then in the middle we have images of Arabidopsis thaliana taken by a camera mounted to a robotic arm in a lab environment. And then on the right side we have our mixed crop plots from drones you're already familiar with. And the goal of the first part is now to generate a new artificial image only based on one image of a previous growth stage. And to understand how this works, it's time to dive a bit more into details. So the problem of image generation is really a long-standing problem in computer vision and became really a boost when Ian Goodfellow invented the Generative Adversarial Network, or short GAN, in 2014. And with this, given some real images of crop mixtures, it was suddenly possible to generate new high-resolution images just from a vector of noise, which is typically Gaussian noise. And we can also extend this approach by including class labels. For example, we can force the model to only generate wheat images. And this is this extension we now call conditional GAN. And as you can see on the right side, now only wheat images are generated by the model and not mixtures anymore. So another extension is that the condition does not only need to be a class label, but can also be an image. And here, for example, the task is to colorize the gray input image into a RGB output image. And our model then gets slightly more complex since we need an encoder first, which compresses the gray input image into a so-called latent space, typically use of convolutional layers. And then we have a decoder part, which does exactly the opposite and just decodes from the latent space to the final image. But unfortunately, it's not that simple because in the beginning, the generated images do not look realistic at all. So we need to train our model first. And for this, we need a second neural network, which is the discriminator. And the task of the discriminator is to decide if the generated images look real or not real. So it is presented alternately, the generated and the reference image, along with the gray input image. And then it outputs a score between 0 and 1 if it thinks that the input is real or generated. And then by optimizing both networks together in an adversarial manner, and this is the real core of the GAN approach, it can produce high resolution images. So during training, we try to minimize an objective function with a generator, and at the same time, in an adversarial manner, we try to maximize it with a discriminator. Simply speaking, I would say the discriminator gets better and better in detecting generated images, and by this, the generator gets better in producing more accurate images, which can then fool the discriminator in the end. So this GAN framework has been used for several, or not only GANs, but image generation in general has been used for several classic image-to-image translation tasks. And image-to-image translation is the process of transforming one domain into another domain. And where the goal is basically to learn a mapping between both domains. Typical examples are colorization, as you have already seen. Then the super resolution is another example, the style change, or even a segmentation tasks. But all these approaches you can see here have in common that there's no time shift between input and output image. So our question is, can we also apply this model, or can be image-to-image translation be done also with the temporal domain shift? And to demonstrate the difficulties here, I would like to switch to the cauliflower dataset. So compared to classical image-to-image translation, there are significant structural differences between both images. So the cauliflower head 3 weeks later has completely different shaped leaves, and also the background, when you have a look on the irrigation pipes there, are not stable. So our goal was to build a model that predicts the cauliflower plant 3 weeks in the future, but not only for one selected time step, but for all possible 3-week time steps in this data set. And to make it a bit more challenging, there are different treatments in terms of fertilization and irrigation over the growing period, which we categorize into good, medium, and poor treatments. And this is then how the results look like. On the left side, there are the input images, in the middle, the generated images, and on the right side, the corresponding reference images. And as you can see, the generated images overall and really also the cauliflower head inside look quite realistic. Of course, you can still measure some quality differences, and you will also find some blurrings and unnaturally shaped leaves. But the overall impression, I would say, is quite good. And if you now if you now have a closer look and compare the plants really leaf by leaf, you will find that the generated plants do not really match the reference plants. So apparently, there are not enough information in the very early growth stage, 1 week after seeding, to generate the correct output image. But then we ask ourselves, is the model here doing really a bad job? Is it really less accurate, or is it still another possible above ground plant phenotype, what is here generated on the left side? And to evaluate this hypothesis, we did a plant trait-based evaluation. So we calculated the projected leaf area, which is the sum of the leaf area you can see from a bird's eye view from the reference plants, but also from the corresponding generated plants. And then we just compared this for the different treatments and for the different weeks. And on the left side, you can see the projected leaf area over time for all the real plants, and on the right side for all the generated plants. And so when you look on the left side, you can see that the projected leaf area is quite realistic, which means that good treatment plants are larger than medium and poor treatment plants. And luckily, when you switch to the right side, you can see the exact same trend also there. This is really great because we generated these images without explicitly taking the treatment information into account. So this means that the model itself has recognized that the plant of a poor treatment was taken at the input side, and that this plant is slightly smaller in the early growth stage, and this then made the plant to be also slightly smaller 3 weeks later. So really, without providing the model with any additional information about the treatments, the patterns in the images itself are enough to model different plant sizes under different conditions. And also, we have shown here that we can bridge a temporal domain gap with image-to-image translation very well. But of course, we still have some limitations. Behind the model is the assumption that the factors of influence are already represented in the image, which is certainly not always valid. And second, the model can only handle one input and generates one output. And this is also not super cool. So this is what we try to tackle in the next part. And here we develop a model which can generate multiple output images from a sequence of input images. And there's also some related work to this, for example, to forecast the spread of a disease based on a time series of affected plant leaves, or to forecast in the middle the development of a plant root system, or to even model the above ground plant phenotype. But all these methods have in common that they all rely on equidistant and complete time series. So equidistant means that there's always the same time interval between each input image, and complete means that the model input sequence need to have always the same length. So when you now have a look on the sequential data sets I used during my thesis, the equidistant assumption is not always fulfilled. So the number over the images is the day after seeding. And of course, there are data sets where it is fulfilled. For example, the Arabidopsis data set in the top row. But then when you have a look on the on the real data sets, like the grow flower and the mixed CKA data set, it is not fulfilled at all. And this is because non-equidistant sequences are even more useful in practice, because it makes much more sense to fly more often over the field when the crops change drastically than in the early growth stages. Moreover, it's very inconvenient if you have a model taking always, let's say, 3 images to predict the future growth, and then you realize that unluckily on one day something went wrong and the model now does not work anymore because it always expects exactly 3 input images. So we really aim for a model which is flexible with a number of input images and can here, for example, also take 2 or just 1 input images to generate a full output sequence. And to achieve this, we take our non-equidistant sequence and compress it into a so-called spatio-temporal latent space. For this, the sequence is first spatially embedded with convolutions, and afterwards temporally with transformer within the encoder of the network. Whereby the critical part is really the transformer layer, which is suitable to process sequences of different lengths, also with additional positional encoding for the non-equidistant time points. And that's why not only the image sequence itself, but also the growth stage, so the time is an input to the model, as you can see here in the formula in the bottom. And then by just iterating over the time, we can generate arbitrary output images. And one thing I did not mention so far, by running the same model with different noise initializations, we can also generate a distribution of possible outcomes for each growth stage, which gives us these nice images, which we call then predictive variability. So we just run the model with for the same time step with 10 different noise initializations, and then we calculate the standard deviation of these runs and visualize it. And this is what you can see here now on the right side. To maybe get a better intuition about the latent space I was talking about, this figure might help. So we have the input sequence on top, which encode the which is encoded into this so-called spatio-temporal latent space. You can imagine that the trajectory represents the growing period, and for some days there are data gaps. And the width of the trajectory is then the spatial variability of a plant at each time point. So, and finally, from this trajectory, you can easily generate or sample and then generate new output images. And really pick specific growth stages you are interested in. So in other words, we can perform kind of arbitrary inter and extrapolations. In this figure, the input images are the ones on in the bottom. So the input images are the ones with the blue frames, and the other ones are just reference images. One row higher is our approach, and on top you can see a variational autoencoder approach. As you can see, like both results are quite promising, with the autoencoder producing slightly more blurry images, which you can see in the higher variances around the leaf edges. But the key difference is really when you look on the extrapolations, and these are not really intuitively doable with classic autoencoders, but our models still produce very reliable results here. So the plant continues growing in the future for forecasting tasks, and is smaller when you extrapolate into the past. Also looking on the images of the predictive variability, it's really quite good. that the variability is higher on the leaf edges where the actual growth happens compared to the other plants, to the other plant parts. So to wrap this paper up, with this model, we can integrate really a whole sequence as input, which can have a variable length. And we can also generate an arbitrary output growth stage, including inter and extrapolations. And also we can visualize the predictive variability. So coming back to our limitations, we still didn't include the factors of influence in the model. And this is something we want to tackle in the last paper when we do multimodal image generation, which is really quite new for the application of crop growth modeling, I would say. And as I said in the beginning, it's really impossible to take all factors of influence into account because there are just too many factors. So in our paper, we focus on the main factors that we have considered in our field experiment at CKA and Wiesengut, which are the cultivation system and the spring wheat and the fava bean variety, and also the seeding density. Time is also still a condition, although we no longer have a sequence in the input, but we still want to be able to actively control which images are generated in the output. And we also add the expected biomass for both crop species. So these two factors are really not influencing factors, but it represents a link into the process-based approach where this data are coming from. And this is the way we include the factors into the model. We take the influencing factors up to the time step of the input images. We perform an embedding and use this embedding as conditional input for the encoder part of the network. And then we take influencing factors up to the time step of the image to be generated, embed them to the decoder part of the network, and then, just generate the new image. In this example, only the time has changed. And with this, also, of course, the expected biomass changed because the data-driven, the process-based expected biomass is coming from the SimPlace model. And this is, there we have like daily measurements, daily output values. But now we can also try to visualize how the field maybe would look like if parameters are changed a bit. So you can see a slight change when we, for example, increase the expected spring wheat biomass and the fava bean biomass. And I think when I go a bit back and forth, you can see also the differences in the generated image. And that is what we call simulation at this step. And with this simulation capability, we can really do some very interesting experiments. For example, first, because we only have one input image now, we can demonstrate that we can still generate different growth stages by fixing all the other factors except time. So here in this figure, you can see in the top row, and now the reference images, with again, the blue framed image is the input image. Then the second row is the generated image. We have in the third row the predicted variabilities, and in the bottom, two classic evaluation metrics comparing the generated and the reference image at each time step, with the red LPIPS curve having its optimum at 0, and the blue multiscale structural similarity curve having its optimum at 1. So first you can see that the image quality decreases with increasing prediction step, which is quite reasonable. You can see that the identity mapping, so the generation of the same time point, has the highest accuracy, which is also expected. But also in the direct neighborhood, for example, when you look at the little hole there on the top right corner, this features are also preserved in the direct neighborhood of the generated images. So it's still, yeah, it's just still visible also in neighboring generated images. And in the end, some weak clusters, for example, at day after sowing 117 and 119, some weak clusters are generated, which are not there in the reference images at all. So it's still not optimal. So when we go too far in the future, the model is not working well. And this can have several reasons. Also, the variance is very low in the end, and it's another thing which could be improved, because, yeah, like when you do a prediction about 70 days into the future, like 10 weeks into the future, I would expect that the model is a bit more uncertain about how the plant will look like. But this is we want to try to tackle in other papers. We also investigate if the image quality benefits from multimodal conditioning. And for this, we take the growth estimation model from the beginning and just regress the biomass from the images. And we do this also for the generated images and for the reference image. And then we just compare and calculate the mean absolute error. And luckily, we can observe that the error decreases the more factors we include into the model. So, and that confirms somehow that the factors of influence really make a difference on the generated image and it have really a positive impact, which we also expected. And with this, we can really now move on to the fun part, really the actual simulations. For this, we fix 3 different growth prediction steps. The first column is the input image. The second one is the reference image for a mixture between spring wheat type Annabelle and fava bean type Mayori seeded in low density. And we can directly compare this to a prediction with exactly the same parameters. So these 2 images look very similar. But we can also simulate what changes if we would have planted, for example, fava bean type fanfare or planted in high density. And for example, what would have changed when we changed the cultivation system to fava bean monocultures or to spring wheat monocultures. Of course, like some of these simulations are not really realistic, I would say, because it's not feasible to just change the cultivation system after seeding. But these kind of multimodal crop growth models could be also applied in a very similar way to data sets with a lot more different influencing factors like weather data or fertilization. And with this being, I think, extremely useful for farmers in the future. And with this, I would like to wrap up. So in the first part, I've showed you a paired temporal image-to-image translation with just one input image and no factors of influence included into the model. Then we extended this approach to a time series approach, where we generated out of a sequence of images, arbitrary output images, and predictive variability. And in the end, where we did a multimodal image generation, and we were also able to do very interesting simulations, which could be helpful for farmers in the future. Before I end, I would like to give you 2 of many possible future directions. So the first point is very specific. My thesis focuses on GANs, but there's another generative model called diffusion model, which recently became more and more efficient and also applicable for really small scale data sets. And by investigating more in this direction, I believe we could really increase the quality of the generated images even more. And the second point is a bit more general. So since data-driven models are focusing on modeling the past environments, we need to ensure in the future that the model is also capable of including, for example, climate change, because yeah, our model won't just work anymore in the future, or it's still not sure if they work in out of distribution cases, which should be really focused on future image generation for crop growth modeling. And with this, I would like to thank you for your attention. And if you have any questions, I'm very happy to answer.